The third and final part of the lesson on tangency problems will deal with implicit curves. Now, what is an implicit curve? It's a curve given by an implicit equation between x and y. Oh, wait a minute, did I say a curve? It can be a curve, but in some cases it can have more than one pieces. You may very well end up with a group of curves. Here are a couple of elementary examples. These are elementary enough that you have one pieces actually. This one is an ellipse. X squared over a squared plus y squared over b squared equals to 1. And as you can see, this curve fails the vertical line test. It is impossible to solve for y for entire curve, not unless you introduce a symbol like plus or minus square root of something. In that case, you have double valid functions, so it doesn't really work very well. How about this one? This looks even more complicated. This curve is called Descartes volumes. It has some historical importance. Here it is. This curve fails vertical line test 2. Consequently, it cannot be solved and then made into explicit form. So, it is impossible to get an explicit form, so in order to find out the tangent line, the derivative computation has to be done implicitly. What do you mean by an implicit differentiation? Let's explore it through a couple of examples. And then, if we have some time, we'll talk about theoretical background on it. Please be warned, theoretical background can be a little bit difficult in this case. Let's go with the first example here. We have this curve, and then let's find out an equation of the tangent line at x equals to -2 and y equals to 1. If you want to check whether x comma y equals -2 comma 1 is indeed in this curve, you can plug those x and y values in. Do we have this equality? Do we have 1 equals to 1? Well, it'll turn out that way. I'll leave that to you. And let's go over to the solution. Here it is. The derivative of x squared is 2x. That was easy. No problem there. What is derivative of 3y squared? It's 6y. That was easy too. But here's a problem. What do you mean by implicit differentiation? Whenever you take the derivative with respect to y, you have to multiply by y prime. That is the essence of the implicit differentiation. We're going to talk about the theoretical background on it later on. As of now, let us get ourselves familiar with this implicit differentiation technique. Let's go over to this again. 3y squared, taking the derivative, you get 6y. But with this to y, so we need y prime. Because I want to emphasize y prime, I wrote red font here. The next one, how about 2xy? This is going to be a product rule, a product of two functions, 2x times y. So let's use a product rule. uv prime equals u prime v plus uv prime. The derivative of first function is 2 times the second function y. And the first function, that's 2x. The derivative of y, 1, but this is implicit. So y prime is multiplied in the end. The derivative of x is 1. And the derivative of 1 constant is 0. So what do we have? We successfully differentiated the given equation implicitly. Step 1 is done. Now that the step 1 is done, we can plug in the numbers. X equals to -2 and y equals to 1. Do it. Oh, one more thing. X is -2, y equals to 1, and y prime is the slope m. and I want to emphasize this, so I'm using the red font here. So plug in the numbers, and a little bit of computation yields this very simple linear equation. And solving this linear equation is just basic algebra. We end up with m equals 1/2. What does that mean? Slope of the tangent line is 1/2. So putting everything into slope point equation of the line, 1/2 x minus of -2 plus 1, or 1/2 x plus 2 plus 1. Breaking up this parentheses and simplifying, we are going to get slope-intercept equation. The latter part of the problem was just easy algebra. After plugging in, solving an equation, again was an easy algebra. The difficult part is the implicit differentiation. It needs a little bit of exercise, so let's do this a couple of more times. Oh, by the way, here is Mathematicas justification. Here's a curve and then a tangent line. Slope is 1/2 and then runs through 0,2, the y-intercept. Let's look at another equation. How about this one? This looks interesting to me. The reason I like this is because of this part. This parenthesis square, so this is a composite function. So please prepare to use the chain rule here. Let's go. The derivative of x squared is 2x. That was easy. Derivative of 8y squared is 16y. That was easy too. But remember, whenever you take the derivative with respect to y, we have to have y prime. That is the essence of the implicit differentiation. That's why I emphasize y prime in color red. Let's go over to the right hand side. We have a composite function, so let's use chain rule. 2 comes out, nothing changes inside. Subtracting 1 from the power, we have just first power. That's why we don't have anything. And the final part of the chain rule, the derivative of the inside is going to be multiplied. What's the derivative of 2x squared? 4x. That was easy. What is the derivative of 2y squared? 4y. That was easy too. But then again, don't forget this y prime, the essence of implicit differentiation. Now, how do you deal with x cubed? 3x squared. Okay, now that the differentiation is done, let's plug in the numbers. X is 1, y is 1, and y prime, which I emphasize in color red, is my slope m. Put everything in, and we have this simple equation. Some numerical computation, 2 plus 2 minus 1, 3 times 2, that's 6. Okay, here we go. Some further simplification, we have this equation. A little bit further, and we end up with m equals -1/2. After plugging in, this is just basic algebra, no problem there. So from the slope point equation, slope, and then -1 plus 1, we have equation of the tangent line. The problem asks us to find out slope-intercept equation, so break up the parentheses, and then we are going to get slope-intercept equation. Let's see. What does a graph look like? Oh, that looks interesting. Oh, wait a minute. This is one of those examples where we have 2 or more pieces. We have this piece, and then we have another piece there, and then 1, 1 is in this piece. We have a tangent line there. Slope is -1/2. Okay. and then running through 1.5, 3 halves. Okay, everything fits. Interesting picture. Let's do it once more. Let's go over to this example. This time we're going to have to use chain rule over here, product rule over there. Ready? Go. 2 comes out and nothing changes inside. And first power, okay, so we don't have to write first power. By the chain rule, the derivative of the inside is going to be multiplied. So x squared becomes 2x, y squared becomes 2y, but don't forget y prime, the essence of implicit differentiation. 2y becomes 2, but then again we have y prime. How about the right hand side? 8xy. The derivative of first function is 8 times the second function. The first function 8x times the derivative of the second function. Derivative is 1 if you take the derivative with respect to 1, y, but y prime pops out. Again, this is the essence. That's why I emphasize them in color red. Now, plugging all the numbers, x equals to 0, y equals to 2, 0, put it in there, minus 4 plus 4. Oh, this is 0 times something, so left hand side is 0, right hand side is, wait a minute, what do you have? 0 equals to 16. Let's check. 8 times 0, that's 0. 0 minus 4 plus 4, that's 0 times something. Yes, 8 times 2 is 16. We have 0 equals to 16. We didn't do anything wrong. What does that mean? That simply means m is undefined. This entire thing is invalid. Now, what kind of line has no slope? It's a vertical line. We have to have vertical line x equals to 0. Let's see the curve. Here it is. Because on the coordinate axis will stand on its waist, I use frame here. This is a point 0, 2, and then we have a vertical line as a tangent line. Alright, as we announced before, let's talk about some theoretical background of implicit differentiation. Why do we have those y primes? Let's go over the first example we did. Here's a problem. Let's copy that. Here, important point is notice that y is actually a function of x, at least locally. Therefore, if you take the derivative with respect to x of this y of x squared, this is a composite function. Again, y of x is a function. Therefore, if you take the derivative, we're going to get something like this. So, derivative of x squared is 2x. That's fine. However, if you look at the next one, derivative of 3y of x squared, this is y of x total quantity squared. So that's a composite function. So by chain rule, 2 comes out, subtracting 1 from the power, so 6 times y of x to the first power. And you have to multiply the derivative of the inside. Derivative of y of x, y prime of x. That's why y prime is popping out by the chain rule. Same thing goes over here. By product rule, 2x becomes 2, and then the second function, no change. The first function stays the same. Derivative of the second function, y of x becomes y prime of x. Again, we're taking derivative of y of x. That's why we have to have this y prime popping up all the time.